So let's look at the discriminant. The discriminant of ax squared plus bx plus c equals 0 when a isn't 0 is given by b squared minus 4ac. Now the following conditions on the discriminant hold. If b squared minus 4ac is less than 0, there are no real roots, because you can see that the curve doesn't cut the x-axis at all. If b squared minus 4ac equals 0, then the roots are real and equal, and you can see that they touch the x-axis at a single point, so the x-axis is a tangent to those curves when b squared minus 4ac equals 0. And if b squared minus 4ac is greater than 0, then the roots are real and distinct, because it means our curves are crossing the x-axis at two distinct points. And that's when b squared minus 4ac is greater than 0. So these conditions can be related to the position of the graph of a quadratic. And remember, the discriminant is a positive square number, then the roots are real and rational. And if the discriminant is positive but not a square number, then the roots are real and irrational. So our example, we want to find p given that 2x squared plus 4x plus p equals 0 has real roots. Now, the first thing we want to do is state what the condition for our discriminant is for real roots, and we know that b squared minus 4ac is going to be greater than or equal to 0. Now we need to work out what our a, b and c values are. So a is 2, b is 4 and c equals p, and we're going to substitute that in to our b squared minus 4ac and get 4 squared minus 4 times 2 times p is greater than or equal to 0. So 16 minus 8p is going to be greater than or equal to 0. And then rearranging, we're going to get negative 8p is greater than or equal to negative 16. Now we need to remember our rules of dividing by a negative term with an inequality. We're going to flip the sign. So if we divide by negative 8, we're going to end up with p is less than or equal to positive 2. The next example, we want to find q given that x squared plus q minus 3x plus q equals 0 has no real roots. So the condition for our discriminant for this example is going to be b squared minus 4ac is less than 0. So in this example, a equals 1, b equals q minus 3, and c equals q. And we're going to substitute those values into our discriminant, and we're going to end up with q minus 3 all squared minus 4 times 1 times q, and that's less than 0. We're going to rewrite the q minus 3 all squared bracket as q minus 3 upon q minus 3, and then we subtract 4q, and that's less than 0, and expanding the bracket gives us q squared minus 6q plus 9 minus 4q is less than 0. Collecting our like terms, we get q squared minus 10q plus 9 is less than 0, and now we need to factorize. So we're going to get q minus 1 upon q minus 9 is less than 0. Now we need to draw ourselves a sketch of what this curve might look like. So we know that it's a positive x squared, so it's going to be a minimum turning point, and our roots are 1 and 9. So sketching that in, if we want values that are less than 0, so that we have no real roots, then the values are going to be in between 1 and 9. So our solution for q is going to be 1 is less than q, which is less than 9. So the next example, we want to find k given that k minus 2 upon x squared minus 3k minus 2 upon x plus 2k equals 0 has equal roots. So our condition for our discriminant for equal roots is b squared minus 4ac equals 0. Now a in this example is going to be k minus 2. B is going to be equal to negative of the bracket 3k minus 2, and we can expand that out to be negative 3k plus 2. And our value of c is going to be 2k. So you can see we've got k in all three of our variables this time. So we've got negative 3k plus 2 all squared, minus 4 multiplied by k minus 2 multiplied by 2k, and that's going to equal 0. We're going to expand that minus 3k plus 2 bracket out and get 9k squared minus 12k plus 4. And then we're going to combine our 4 multiplied by k minus 2 multiplied by 2k. We've got negative 8k multiplied by k is negative 8k squared. And the negative 8k multiplied by negative 2 is going to give us a plus 16k. And all of that's going to equal 0. So now we need to gather together our like terms. So we get k squared plus 4k plus 4 equals 0. And we can factorize that to k plus 2 all squared equals 0. And so k is going to equal negative 2 for this quadratic to have equal roots. So for points of intersection between two graphs, the following conditions on the discriminant hold. If b squared minus 4ac is less than 0, there are no points of intersection, so the graphs don't touch. If b squared minus 4ac equals 0, there is one point of intersection, so it means that our graphs will be tangents to each other. Now, finally, if b squared minus 4ac is greater than 0, then it means that there are 2 points of intersection between our graphs. Now, in this example, we want to prove that there are no points of intersection between the line at y equals 3x minus 1 and the curve y equals 2x squared minus 3x plus 4. So for no points of intersection, the condition for our discriminant is b squared minus 4ac is less than 0. Now, in order to determine the values of a, b, and c, we need to equate our two curves together and rearrange to make them in the format ax squared plus bx plus c equals 0. So we've got 2x squared minus 3x plus 4 is going to be equal to 3x minus 1. And we need to move the terms on the right-hand side over to the left-hand side, giving us 2x squared minus 6x plus 5 equals 0. And so now we can say that a is 2, b equals negative 6, and c equals 5. So now we want to substitute these values into the inequality that we've set up with our discriminant. So negative 6 squared minus 4 multiplied by 2 multiplied by 5 is going to be less than 0 if we have no points of intersection. So 36 minus 40 is less than 0, and that gives us negative 4 is less than 0, which is true. So therefore, we've proven that there are no points of intersection between the line y equals 3x minus 1 and the curve y equals 2x squared minus 3x plus 4.